Okay, welcome to Mathematical Structure for Computer Science. This is CS113, also known as Discrete Mathematics. In these lectures, we're going to study matrices, which cover Chapter 2, Section 6 of the course textbook. So our main objective is to go through the definition of a matrix, also matrix arithmetic operations, both addition, subtraction, and also multiplication. Also scalar multiplication. We should also go through the transpose and powers of matrix. How do we transpose a matrix? And also 0-1 matrix. Here we may have a matrix that consists of only 0-1 values, more or less as a binary numeric system. So we may have, again, a matrix with only binary numbers, 0-1, 0-1s, and how we can do at least 2 operations on them. First will be the conjunction, which is multiplication or product, and also disjunction, which is again addition. When we cover the propositional logic and also Boolean algebra, we discuss about the conjunction and disjunction, or AND operator and also the OR operator. We can apply it on, again, a 2 or more matrices. So first we start with matrix objective, or the advantage of matrix, the main reason why we use matrix. Here we say matrices are very useful in discrete structure that can be used in many ways. For example, they are used to describe certain types of functions such as linear transformation, also express which vertices of a graphs are connected by edges. So we're also going to discuss about graph data structures. Edges, a graph normally consists of vertex and edges. Edges will be the line that connects two vertices together. Sometimes we use the term node. So from here, we can say that matrix in computer programming language can be a 2-dimensional array. Matrix, normally the data are arranged in the form of a table, which consists of rows and columns. Now, if we take any programming language, we can arrange a data in a tabular form, in the form of rows and columns, using 2-dimensional array. So here also we're going to cover the aspect of matrix arithmetic that will be needed later in this course, especially when we cover graph. So the definition of a matrix, we say a matrix is a rectangular array of numbers. So in short, I can also say matrix consists of rows and columns. So it's more or less like a 2-dimensional array or a table. We can see an example here. So here we have 3 rows and 2 columns of data. Normally the size of a matrix, the row comes first before the column. So this matrix here, the size is 3 by 2, which means we have 3 rows and 2 columns, not 2 by 3. Always the rows by the column. So we use the term matrices as a plural for matrix. And also a matrix with the same number of rows as columns is called a square matrix. So for example, if I have a matrix 2 by 2, which means 2 rows, 2 columns, it's a square matrix. Or if I have a matrix 3 by 3, 3 rows, 3 columns, is a square matrix. Also, 2 matrices are equal if they have the same size. That is the same number of rows and the same number of columns. So the size of 2 matrices must be the same. Then also the element must be the same at each position of both matrices. So here we say 2 matrices are equal if they have the same number of rows and the same number of columns, and the corresponding entries in every position are equal. So what I mean, if I have another matrix, let's say 3 by 2, And the first element in this matrix is 1, which is first row, first column. The second matrix, the first element, first row, first column also must be 1. So if I reach second row, second column, which is 2, I have to have the same 2 in the second matrix, second row, second column. So the size must be the same. That's the same number of rows, the same number of columns. And also the element must be the same at each position. So this is the notation for a matrix. Here we are using the uppercase A as the matrix name. So we have matrix A. The size of this matrix will be m by n. We have m is the first character we are seeing here. So that means we have m rows and n is the second character, which means n columns. So m by n means m can be any number, n can be any number. But from this notation here, the size of this matrix will be m by n. So we can see our first, since the matrix name is uppercase A, the notation we use for the elements are lowercase a. And each 2 digits here represent the position of the element. And again, the row comes first and the column comes second. So 1, 1 means the item is in the first row and also the first column. Let's say 1, 2 means we're still in the first row, this time second column. 2, 2 means second row, second column. So here we say the ith row of A is the 1 by n matrix. Remember the I is the first, so that will be the row. So we have I1, I2, up to In. So we have n columns. But again, the I represents the row. And also the jth column of A is m by n. So the columns again, 1j, 2j, etc. And also the ijth element or entry of A is the element ij. I represent the row, j represent the column. As example here, A21 means second row, first column. So we go next with the matrix arithmetic. We are doing addition. Now, in order to do addition of 2 or more matrices, the size of the matrix must be the same. That's the only condition we have. The size of the matrix must be the same. So the example here, we have to check the size. We have 3 rows, 3 columns. So the first matrix, the size is 3 by 3. The second matrix also is 3 by 3. Okay, if that's the case, we can add the 2. Now, when we are adding, we are going to add the exact position of each element. So for example, the first matrix, the first row, first column is 1. The second matrix, the first row, first column also is 1. So I'm going to add the same position, first row, first column, first row, first column. Next, I'll go to the second row, first column. I'll add it to the second matrix of the same position, first row and second column. Next, I'm in the first row, I'm in the third row, first column. Third row, first column. So which means the second matrix, same position, third row, first column. So it will be 3 plus -1. Now let's assume we're on the second row and the third column, which is -3. I can only add -3 at the same position of the second matrix element, which is what? Second row, third column, 0. So -3 plus 0 will give me -3. So again, addition of a matrix, the first thing, the position of the element, we add it to the same position of the element. But before that again, the size of the matrix must be the same. That is the common thing we have to follow. The first rule, actually, the size of the matrix must be same. Then as we said, the position of the element, we have to add the same position of of the second element. So let's see how we get this answer here. First 1 plus 3 is 4. So that first row, first column, first row, first column, we add them together, 1 plus 3 is 4. And I'll go to the second row, first column, 2. Second row, first column, 1. 2 plus 1 is 3, so we have 3. Then we go to the third row, first column, 3. The second matrix, again, third row, first column, negative 3. 3 plus negative 3 will give me positive 2, so we have 2. Then we move to the first row, second column. First row, second column, so 0 plus 4 will give me 4. First row, third column, negative 1 plus negative 1 will give me negative 2. Second row, second column, 2 plus second row, second column, negative 3. 2 plus negative 3 will give me negative 1. Then second row, third column, the first matrix. Second row, third column, the second matrix is 0. Negative 3 plus 0 is negative 3. Third row, third column, 0. Second matrix, third row, third column, 2. 0 plus 2 is 2. So again, that's the steps for adding two matrices. And we can add 2 or 2, 3, or any amount of matrix. So next we go to the matrix multiplication. In matrix multiplication, our rule said the size decimal. Addition, we say the size must be the same. In multiplication, what we are going to say is that the first matrix columns, the number of columns, should be the same as the second matrix number of rows. So we can see these two matrices here, the size is not the same. The first matrix, the size is 4 by 3. We have 4 rows, 3 columns. The second matrix is 3 by 2. We have 3 rows, 2 columns. The sizes are not the same. But in multiplication, the only rule that we follow is that the first matrix on my left, the number of columns should be the same as the second matrix on my right. So I have 3 columns on my left, the first matrix. The second matrix, I have 3 rows. Okay, then we can add it. We can multiply. We can do our multiplication. Why? Because the first matrix, we have 3 columns. The second matrix, we have 3 rows. So we can be able to multiply. Now, let's say in mathematics or arithmetic, we know 2 times 3 is 6. And 3 times 2 is still 6. But in matrix, sometimes we may have first matrix times second matrix. It may work. But if we change the position and we bring our second matrix as first, it will not work. We cannot do the multiplication because the condition that we have to meet, which is the first matrix number of columns, should be the same as the second matrix, the number of rows. In this case, it won't work. So if my matrix, the size 3 by 2 is the first matrix, the number of columns is 2. And my second matrix, the number of rows is 4. So 2 and 4, they are not the same. But the way we have it now, the number of columns is 3, the number of rows is 3, so we can be able to do multiplication. And sometimes if we have a square matrix, it doesn't matter. Square matrix means the number of rows and number of columns, they are all the same. So we can do matrix A times B or B times C, B times A, but the answer will not be the same. Again, that is matrix, the answer will not be the same. Let's say 6 times 2 is 12. 6 times 2 is 12. 2 times 6 also so 12. But in matrix, if we have 2 square matrix, A times B is not the same as B times A. We will get 2 different answers. So how do we get the 14 here? Let's go through this step. What we do is that we take the first row of the first matrix, multiply by the element on the first column of the matrix. You see that they are 3 by 3. That's why we said again, the number of columns should be the same as number of rows. So what we do is that we take again, the position is very important, same as addition. We take 1 times 2. They are in the same position. 1 times 2. The answer is 2. Plus 0 times the next element, which is 1. The answer is 0, so plus 0. Then the last will be 4 times 3, which is 12. 12 plus 0 plus 2 will give me 14. So that's why we have 14. Why 14 is the first, it's in the first row, first column, because we use the first row and the first column of the second matrix to do our multiplication and addition. So now if I take the second row of the first matrix and take the first column of the second matrix, that means that answer we get should be at the second row and first column, which will be 8. So let's try that one. 2 times 2 is 4. 1 times 1 is 1. 1 times 3 is 3. 3 plus 1 plus 4 will give me 8. So that's why we have this 8. The same thing, I move to the next. Why do we get 7? 7 is in the position of what? The first column and the third row. So which means we're still using the first row here. And we are, this time we are using, also, no, we want to do the 7. So if we want to do the 7, we have to use the third row and the first column. Now, if I do the first row and the second column, I'm going to the 4. Because 4 is in what? First row, second column, and 4 is in the position of what? First row, second column. But this, I want to get 7. 7 is in the position of what? Third row, first column. So I will do the third row and the first column. So 3 times 2 is 6. 1 times 1 is 1. 0 times 3 is 0. So 6 plus 1 plus 0 will give me 7. Then if I want to get the fourth row, first column, then I'm going to do the fourth row of the first matrix and the first column of the second matrix. 0 times 2 is 0. 2 times 1 is 2. 2 times 3 is 6. 6 plus 2 is 8. So we get 8. Now I want to get 4. This 4 is in what? The first row, second column. So we take the first row of the first matrix. This time we take a second column. 1 times 4 is 4. 0 times 1 is 0. 4 times 0 is 0. So it will be 0 plus 0 plus 4, which will give me 4. I want to get 9. 9 is in the second row, second column. So I'll go to second row, second column. 2 times 4 is 8. 1 times 1 is 1. Times 8 is 9. 1 times 0 is 0. 9 plus 0 is 9. Then the next one, I take the third row, second column, which will give me 13. 3 times 12, 3 times 4 is 12. 3 times 4 is 12. 1 times 1 is 1. 0 times 0 is 0. So 12 plus 1 plus 0 will give me 13. And the last one will be fourth row and second column. And that's 2. 0 times 4 is 0. 2 times 1 is 2. 2 times 0 is 0. 0 plus 2 plus 0 is 2. So again, that's how we do our multiplication. First, we check the first matrix number of columns should be the same as the second matrix, the number of rows. In this case, we meet the condition. That's it. Next, we take the first matrix rows by column throughout. So this is an illustration of the matrix multiplication. So we can say we have matrix A and B, position from A11 to AMK, which means we have M number of rows and K number of columns. We have a second matrix from B11 to BKN, which means, again, we have K number of rows, N number of columns. So if I want to multiply A by B, the first thing I'll look, how many columns I have? K columns for the first matrix. So I have to have K rows for the second matrix. So that's K. So that's why it's KK. K number of rows, number of columns is the same as the second matrix, K number of rows. The first matrix number of rows should be the same as the second matrix number of columns. So A, the number of rows is K. B, the number of columns also, the number of rows also is K. Okay, if that's the case, we can do the multiplication. So here we say AB will give us the answer here, which will be A11 times B11 plus A12 times B21 plus the last one, A1K times BK1. And we keep going. Then we take the same first row, second column, first row, third column. Keep going. So this is what we said earlier. The matrix multiplication is not commutative. I have two square matrices, which means I can do A times B. I can also do B times A, but the answers will be different. So when we do A times B, we get 2, 2, 5, 3. Let's see the reason why. I take the first row of matrix A and then multiply with the first column of matrix B, and that will give me the first element of the solution. So 1 times 2 is 2, plus 1 times 1 is 1, 2 plus 1 is 3. And this is supposed to be 3. Then we take same first row again, this time second column. 1 times 1 is 1, and another 1 times 1 is 1. Again, 1 plus 1 is 2, so we have 2 here. Then we go to the second row, first column. 2 times 2 is 4, 1 times 1 is 1, 4 plus 1 is 5, so we have 5. And the last will be second row, second column. 2 times 1 is 2, plus 1 times 1 is 1, and that will give me 3, so we have 3. Now, when we do the BA, we have to take the first row of B multiplied by the first column. When we're doing AB, we take the first row of A multiplied by first column of B. Now, when we do BA, the first row of B to the column of A, so opposite. So here you can see that we get 2, the first row, 2, 2, 2, 1, and also 1, 2. So we get 4. And I'll even stop, because when we look at AB, there's no 4. So if I have 4, we should get 3. And also, let's see here why we have 2, but here is 3. So here means I'm going to take the second row and second column. So my second row is 1, 1. Second column also is 1, 1. 1 times 1, 1 times 1, they are 1, 1. 1 plus 1 again is 2. But AB is 3. So again, based on this, we can see that AB is not equal to BA. Anytime we have a square matrix, we can multiply either one first. We can say A times B or B times A if it's square matrix. So also we have what we call the identity matrix and also powers of matrix. Now, identity matrix means all the elements in the matrix are 0 except the diagonal, which means if the index, if the row is the same as the column, then it's 1. So here you can see that matrix in the position 1, 1 is 1, 2, 1 is 1. And the second one will be column 2, row 2. So 1, 1, 2, 2, 3, 3, 4 to the end. And that will be diagonal. So an identity matrix of order n is the n by n at matrix In equal to sigma ij. But this time, the position of the element sigma ij is 1 only if I equal to j. So in the position 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, all the value there will be 1. And that will be the diagonal, all will be 1. Then the position sigma ij is equal to 0 if I is not equal to j. So for example, A 1, 2, or 3, 1, or 3, 2, or 5, 6. As far as it's not 6, 6 or 5, 5, it should be 0. So an example of identity matrix is what we have here. Normally, we use the identity matrix in system of linear equation in linear algebra to find a system of linear equation. Using matrix, we have to find the identity matrix of the coefficient x, y, z. Then whatever value we get in the constant row, that'll be the answer for x, y, z. Again, in this course, we are not doing that. The only thing we should know is what is identity matrix. Also, the powers of matrix is the same as an exponent. So we know that a matrix raised to the power 0, the answer will be identity matrix. That's what we have here exactly. Doesn't matter, A can be any value. If A raised to the power 0, then we have identity matrix. Now, A raised to the power R means we are going to multiply the matrix R times. So if there are, let's say, A raised to the power 3, it means I'll multiply the matrix, original matrix by itself 3 times. Or if R is 10, that means 10 times. But always, if the identity matrix is raised to the power 0, if the matrix is raised to the power 0, the answer will give us the identity matrix. So next is transpose of matrices. To transpose a matrix, we change the row to column and then column to row. So example here, they say we should transpose the matrix 1, 2, 3, 4, 5, 6. The size of this matrix, we have 2 rows, 3 columns, so it's 2 by 3. Now, when we transpose this matrix, all the row becomes column. So 1, 2, 3 become 1, 2, 3. Instead of row, is column. 4, 5, 6 becomes 4, 5, 6. By this time, also it's a column. The same thing the opposite way, we can change column to row. When we are finding a transpose of a matrix, change the columns to row or change the row to column. So a square matrix A is called symmetric if A equal to A transpose. So let's see this example. Sometimes we may have a matrix. When we transpose the matrix, we get the same result. So matrix A, when we transpose matrix A, change the rows to column or column to rows, we will still get the original A. Example given here, yes, this is a symmetric matrix. Why? If you change 1, 1, 0 as a row to column, you will get the same 1, 1, 0, which is here. Now we are in the second row. The second row, we have 1, 0, 1. If we change the second row 1, 0, 1 to the second column, we still get 1, 0, 1. Then we are in the third row. Third row, we have 0, 1, 0. If we change it in the third column, from row to column, it will be 0, 1, 0 also. So this is again a symmetric matrix. Because if you change the rows and the columns, you will come back to the original function, or in this case, the original matrix. So here we say square matrices do not change when their rows and columns are interchanged. Also, we have the 0, 1 matrix. So a 0, 1 matrix means a matrix with binary numbers. So a matrix, all of whose entries are either 0 or 1. A matrix, all of whose entries are either 0 or 1. It's called 0, 1 matrix. This will be used a lot in chapter 9 and 10 of our course textbook. So the algorithm operating on discrete structures represented by 0, 1 matrix are also based on Boolean arithmetic defined by Boolean operation, which we cover in chapter 12. So for example, we know this operator is conjunction or product. So B1 conjunction B2 is equal to 1. Only what? If B1 is 1 and B2 also is 1. Remember 1 times 1, or 1 conjunction 1 is 1. the rest is 0. So 1 conjunction 0 is 0, 0 conjunction 1 is stays 0, 0 conjunction 0 stays 0. So we say otherwise is 0. We only get 1 when both of them are 1. Now with disjunction it's opposite. We only get 0 when both of them are 0. Otherwise the rest is 1. If it's only 1, we still get 1. If it's both of them 1, we still get 1. If the opposite of the 1, we still get the same 1. So here we say B, disjunction B1, disjunction B2. We get 1 if only B1 is 1 or B2 is 1. Otherwise, we get 0 if B1 and B2 is 0. So that's the definition here, which is almost what we just explained. So we say let A be Aij. So Ij is the subscript for the position of the element. And we have matrix B, whose subscript also is Ij. So we can have a matrix n by n with all the elements is 0, 1. Now the join of A and B is a 0, 1 matrix with Ij entry as Aij, disjunction Bij. So the join of A and B is denoted by, again, I disjunction B. Now the meet of A and B is the 0, 1 matrix with an entry Aij conjunction Bij. So if they say we should find the meet of A and B, we just have to find again conjunction of A and B, matrix A and B. This is if the two matrices are 0, 1 matrix. We are using binary number system. So we'll see example here. Here they say find the join and the meet of 0, 1. So to find the join, we know we have to find what? A disjunction B to find the join. So the positions are the same again, like addition. So 1 disjunction 0, same position. Then we have again 0 disjunction 1. Then we have 1 disjunction 0. Then 0 disjunction 1, 1 disjunction 1, 0 disjunction 0. And that's what we have here. Multiply each element, whether multiplication or addition, conjunction, disjunction, the same we do. So from here we know 1 disjunction 0 is 1, addition. 0, 1 also is 1, 0, 1 is 1, 1, 1 is 1. We only get 0 if all of them are 0, 0. So finally, our answer will be 1, 1, 1, 1, 1, 0. So how do we get this again? Look at the size here must be the same. Look at the position of each element. It's like doing addition. 1 and 0, 0 and 1, 1 and 0, 0 and 1, 1 and 0. The last is 0 and 0. And all of we are looking for the join. So all of them, there will be operator of disjunction. Join use operator of disjunction, and meet use the operator of conjunction. So the second one, they say find the meet of A and B. So we take the element A and B, 1 and 0, 0 and 1, 1 and 0 again. So 1 and 0, 0 and 1, 1 and 0. Then the second row, 0, 1, 1, 1, 0, 0. So 0, 1, 1, 1, 0, 0. Then I know 1 and 0 is 0, 0 and 1 is 0. With conjunction, if you even have 100 elements, if 1 is 0, all of them will be 0. So here we can see that everything is 0 except 1 and 1, which is 1. So those are again the example for join and meet. Again, join is using disjunction. Meet is using conjunction. But first, before we do that, we have to check the two matrices have the same size. So we can also do the Boolean product of 0, 1 matrix. So here we are saying that let A represent Aij, which is the element of the matrix uppercase A, ij is the position of the row and the column. And here we say this matrix should be an n by k01 matrix. And we have matrix B, and it's k by n01 matrix. Now, to find the Boolean product of A and B, which we denoted by a circle with a dot. So here I'm looking for A, again, Boolean product, not arithmetic product, Boolean product B. So we do the conjunction, 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 then we disjunct all of them. Now let's see how the example work here. Here also you can see that the number of columns is the same as the number of rows in the second matrix. The number of columns in the first matrix is 2. The number of rows in the second matrix is also 2. So this means we can be able to do the multiplication. So next, what we do? We get A and A, or 0 and 0. And let's see why that works. So we take the first row and the first column, same step as what we did in multiplication with decimal numbers. Same thing with the multiplication with binary numbers. So 1 times 1, 0 times 0. When we look here, 1 times 1, 0 times 0. Again, conjunction is multiplication. Then the answer you get for the 2, you disjunction, so which means adding them. Same step as we did previous decimal number system for multiplication of, again, matrices. Let's try one more. Let's go to the second row, second column. So 0 times 1, disjunction, 1 times 1. So that's 0 times 1, disjunction 1 times 1. So after we finish all, then we can do the first one. 1 by 1 is 1. 0 and 0 is 0. So we get 1 or 0, which give me 1. 1 and 1 give me 1. 0 and 1 give me 0. But 1 or 0 will give me 1. Then here 0 by 0 is 0. 0 by 0 again 0. 0 or 0 will give me 0. So again, we do the first row finish. Then the same thing we do for the second row and third row. Now the next is the Boolean power 0, 1 matrix. As we said earlier, R times means you are going to multiply the Boolean by itself R times. So if R is 4, it means A to the power 4 is A times A times A times A. We multiply A 4 times. And remember we said that if R is 0, A raised to the power 0, the result should give us identity matrix. So let's see the example here. We have a matrix A. Now we say for all A raised to the power n, we need to find the positive integers of n. For all possible positive integers of n, we want to find it. So we start with the A. We multiply the A by itself, we get A squared. And that's the result we get. The same step as the previous slide, so I won't go through that. Then the second, A to the power 3. We know A to the power 2 once already, so it's A to the power 2 times A again. And this is the result we get. Then we go to 4. A to the power 3 times A. And this is the result we get. Then we go to 5. A to the power 4 times A. And we get 1, 1, 1. So when we get 1, 1 throughout and no 0, we stop. So here we say our solution will be n is either equal to 5 or more. Because up to 5, that's when everything is 1. So this will be the conclusion of a matrix. In this lectures, again, we learn how to use the matrix in discrete mathematics. First, what is a matrix? And as we said, a matrix is more or less a table, consists of rows and columns, or two-dimensional array. Matrix is used as a data structure also. in computer science. In computer programming, you can declare variable as a two-dimensional, almost the same as matrix. We also talk about matrix operations, arithmetic operations. We can do multiplication. If we are doing multiplication, we have to make sure that the number of columns in the first matrix is the same as the number of rows in the second matrix. Other than that, we cannot do multiplication. Addition means we just have to make sure the two matrices have the same size. Then we can do addition. We also talk about 0-1 matrix, which is the concept of Boolean number system. A 0-1 matrix consists of only 0-1 digits. So again, wish everybody the best and thank you.